Hello, today we're going to talk about the Beer-Lambert law. So when we're experimenting with the Beer-Lambert law, we're going to be using what's called a spectrophotometer. Occasionally you'll use something called a colorimeter, but they work kind of on the same principle. So essentially you'd have a light source inside the spectrophotometer. And sometimes you will put the light through a prism to get like just a specific wavelength passing through. But no matter what, you're passing the light through a sample. And the sample is usually in this kind of squarish container called a cuvette. We want it to be square so that the light is passing through the same distance every time. If we use like a test tube and it's round, it won't have the same distance. Only some of that light is going to pass through the cuvette and through the solution inside the cuvette, and then it will be the light that actually passes through is picked up by a detector, and that will give you an output. So the light that passes through is the amount of light that is transmitted. The light that does not pass through is the amount that was absorbed. And again, you can choose to send like all white light through and just see which color is absorbed the best or the worst. You can also choose to send just one specific wavelength of light or one specific color of light and see how much of it passes through. So that's how the spectrophotometer works. So let's talk a little bit about the different colors of light and how that works in our spectrophotometer. Let's say you have a solution that is blue in color. Okay, it looks blue to us because the blue is being reflected back towards our eyes. That means that it is absorbing really well on the opposite side of the color wheel. So it is absorbing those like red, orange, and yellows, and reflecting back the blues that we see. Excuse me. So again, whatever color the solution looks, it will be absorbing the opposite color of light. Now, if you were to just shine white light, which is consistent of all of the colors, you can use the spectrophotometer to test which wavelength of light has the greatest absorbance. And you'll get a graph kind of like this. So in this case, it looks like the highest absorbance is 620 nanometers for this substance, whatever it is. And so 620 nanometers falls right in orange. Okay. So because it's absorbing orange light really well, we know that the solution must be blue in color when we're looking at it, because it's on the opposite side of that color wheel. So just kind of keep that in mind. That's how it works. So once you've figured out what wavelength that your substance absorbs the best, you want to use that wavelength and just that wavelength in your spectrophotometer with different dilutions of the substance. So this image is an example of serial dilutions of your sample. So since your substance is red, it will absorb the best kind of in like green wavelengths, and you don't need to know the wavelengths, like which color is which by heart. But you want to use like a green color light in your spectrophotometer, and you'll measure how much of the light passes through the solution for each of these samples. Now, the more concentrated, the less light will be able to pass through. I want you to think about it in terms of the number of particles. So if I have something that's really highly concentrated, you'll have lots and lots and lots of the solute particles, and it blocks more light. But if you have a dilute solution, it will have fewer particles, it will block less light. So in this color progression, this one will have the highest absorbance because it blocks the most light, and this one will have the lowest absorbance. You'll also have what's called a blank. A blank will be just your solvent, none of the solute, and that one we're going to say has a 0 absorbance. And you calibrate the spectrophotometer by setting that blank with just the solvent, and you set that to 0. And so then you're relating all of your other substances to that. So let's say, for example, you put all of these substances into your spectrophotometer, you use just that one green wavelength of light, and you record the absorbance for all of them. You will always have, hopefully, a 0, point because you have your blank, but then you'll also measure the absorbance at these different concentrations. And from there, it should be a straight line. Okay. And you can find a line of best fit, and that will give you kind of your relationship between absorbance and concentration. Sometimes we will also call this a calibration curve, because you are calibrating that relationship between absorbance and concentration. Now, the equation of that line of best fit, you're going to wind up with a y equals mx plus b format. But on our y-axis is absorbance, so y is actually A for absorbance. On our x-axis is concentration, so we're going to use C for concentration. And our slope relates both the molar absorptivity constant, which we use this Greek E, and B, which is the path length. Now, this is a different B than the y-intercept. Hopefully your y-intercept is 0. Now, if you have sources of error in your experiment, it might not be exactly 0, but it hopefully will be very close to 0. But then we wind up with this part, which is what we call Beer's law, or the Beer-Lambert law, where A is absorbance, E is the molar absorptivity constant, and B is the path length. So this together makes the slope. But since our cuvettes that we use are usually 1 centimeter, that means that your slope is essentially just the constant there that relates absorbance to concentration, which is super useful. So this is Beer's law, and it, as absorbance increases, concentration increases linearly, and we can use a calibration curve to determine exactly by how much the absorbance increases as concentration increases. So here's an example graph. Absorbance is on the y-axis, concentration is on the x-axis. And so equation of our line, if we use y equals mx plus b, our y is our absorbance, our slope is our b times c, x our concentration, b times e, right, that, and then x is our concentration c. And B should be 0 as much as possible, as close as it can to 0, because you want to set a 0 concentration as a 0 absorbance. So they gave us the equation, and I know it's kind of small here, but they gave us the equation of the line of best fit for those data points. So they told us that our absorbance is equal to 0.113 x, which is our concentration, or C, plus 0. Okay, so this is kind of an idealized graph. So this is our path length times our molar absorptivity constant, and so now we can relate absorbance and concentration. From here we can plug in the absorbance, 0.332 equals 0.113 C, divide both sides by 0.113. To get your concentration, which is 2.94 times 10 to the negative 6th. Sometimes these graphs are easy enough that you can just trace over, find the concentration, and trace down. So you'll see that sometimes too. But this one was a little bit more involved because they gave you the unit as times 10 to the negative 6th, which is micromolar. So we wanted to figure that out there. Either way, you can pretty easily find the concentration from a calibration curve like this.